Hello, today I'd like to talk about Monte Carlo integration. These are the today class objectives. I wish that at the end of this lecture, I wish that you can understand the sampling approach for solving the random equation that we talked about last time. And as a sampling approach, we will talk about Monte Carlo integration, and then we will talk about this Monte Carlo estimator and each bias and variance. In this class, I will talk about I will mainly talk about high-level idea. If you want to know the details about this technique, I recommend you to look further my book. As we mentioned before, the radiance evaluation is the fundamental problem for evaluating global illumination techniques. So at this point, suppose that we wanted to compute basically we have this ray from here to that direction. That we need to compute the radiance value that starts from x to that direction. In this case, theta, right? So basically, this is nothing but evaluate radiance at a given surface point in a given direction. Basically, unless we don't have any participating media along this ray, basically we can have this invariance. So in other words, this radiance does not vary from here to there. So once we know the radiance for a ray, then we can evaluate the ray. We can fully perform the ray tracing. The problem is that there are so many passes. Here, suppose that we want to compute the radiance value from here from the point of x to that direction. Then we need to there could be the infinite number of this path. I mean this light source and the one basically there could be the incoming radiance from here to the x, or there could be one bounce from here hitting this surface and then hitting there. Also, there are another path from here, we intersecting here and there, or there could be this multiple bounce. The light source, the photon emitting from here, hitting there, and then ending up the X here. So there could be so many possible paths. So you probably remember that this is the radiance. This is a random equation in hemispherical formulation. Basically, I will mainly use the hemispherical formulation. So again, basically, to compute the reflected radiance from x to the direction of theta, we need to consider all the incoming radiance over this psi over the hemisphere. Basically, this is the incoming radiance, and then this is a BRDF. And then also we need to adjust the oblique surface, this cosine theta x over the solid angle. So again, there are so many passes. So basically we need to integrate all the incoming direction here over the hemisphere. And then basically analytically solving this random equation almost impossible. Obviously, in some very simple cases, there could be some of the simple analytical solution. But in general case, we don't have the any analytical solution. So as a result, we need to rely upon some sort of approximation over the numerical techniques. Early on, as a numerical approach for solving this kind of complex integral equation, Monte Carlo integration arrived. This is a numerical tool to evaluate integrals. So basically, the Monte Carlo integration simply used the sampling technique. Since it used some sort of random sampling, it has this stochastic error. But basically this unbiased technique, which is very important concept for the rendering. Unbiased means on average we get the right answer. That's the main definition of the unbiased. Since this is sampling technique, so on average means that once we have the infinite number of the samples, basically we can on average we can get a right answer. This one example, suppose that we need to evaluate a simple integral, one-dimensional integral. This is the function f of x defined in the domain from the a to b, and it has this kind of shape. And basically, we want to compute we want to evaluate this integral function, and we want to compute this I value. One simple approach that we talked about before, maybe in the high school, it's a deterministic integration, also known as the quadrature rules. You might remember that we actually discretize this function space with these simple shapes, and then we evaluate. We integrate this area of the subdomains, something like this. So as we had a very small, infinitely small size of this rectangular shape, on average we can get the right answer, right? But this approach is that this determinist approach. Obviously, basically it means that we need to have the infinite number of infinite number of subdomains, which takes a lot of time, right? Instead of that, we wanted to use some sort of the sampling approach. So now I'd like to talk about some of sampling approach. Basically, here I'll talk about primary estimator for Monte Carlo technique, which is nothing but just using the one random samples. Suppose that this is the integration function we want to compute, and primary estimate is nothing but just using we just generate a random number in the range of domain of this function. In this case, 0 to 1. We generate just a random number x bar, and then we just using the x bar this function as a primary estimator. Then basically, if we compute the average of this primary estimator, then we need to integrate. You might remember that you need to recall computing average of the random samples, and then we need to integrate this. We need to integrate this primary estimator. In this case, x bar. In this case, this x actually in the range of 0 to 1. Basically, here actually I used x bar, but we should use the x bar here. But I used the x again here. This is a kind of abuse of notation. And then basically we just use the function the variable x here. And then since this is actually random sample, we need to multiply this primary estimator with each probability. In this case, p of x. So here I used just random uniform sampling. So in this case, p of x is simply 1. Then in the end, this the average of this primary estimator is turn out to be like this, and in the end, it's exactly same to this one here. This is the integration that we want to compute. In this case, a and b turn out to be the 0 to 1. Now let's talk about another example here. Basically, the same simple function, but in this case, domain of this function starts from the a to b, not 0 to 1. And in this case, we define the primary estimator, fx. Actually, I used x sub s, but but here, basically, in this case, the primary estimator defined by I will just simply use f of x divided by the p of x. So in this case, p of x actually turn out to be the p of x turn out to be the 1 over a minus b, which is then f of x and divided by p of x turn out to be fx multiplied by the b minus a here, and then average of this primary estimator turn out to be like this. So we integrate in the range of a to b fx, and then basically we put this primary estimator here. And then also we need to consider when to multiply with the p of x. And as I mentioned before, p of x defined basically p of x nothing but 1 over b minus a. Why? If we integrate basically if we integrate the p of x in this range, that should be the 1, right? If we integrate this value over the a to b, then it should be the 1, right? That's why the p of x is turned out to be 1 over ba. Then these two terms cancel each other. Then in the end, this is nothing but the original integral that we want to compute. So that's why we want to cancel the p of x here. That's why actually we define the primary estimator f of x divided by the p of x. Again, basically on average, our simple primary estimator for the Monte Carlo integration is also the unbiased estimator. Basically, so far we talked about average, but we need to think about what's the error of the Monte Carlo integration. Variance to measure the error of the Monte Carlo integration, we can simply use the variance of the estimator. This is nothing but a measure of the stochastic error. So in this case, the variance is nothing but basically we want to measure the difference between our estimator, f of x divided by the p of x. Basically, the difference between our estimator and the ground truth. In this case, I is the actual ground truth value of the integration function, and basically their distance. In other words, basically we measure their difference and we take the square, and then basically the variance also they're measured by that value multiplied by the p of x in the range of the a to b. Basically, this is the variance equation in the random samples. Basically, there could be many ways of reducing this variance. As an example of reducing the variance, we will briefly talk about important sampling later on. Then we can simply I will talk about the secondary estimator, that also simply using the primary estimator multiple times. But this is actually typically basically this is the typical estimator that we are using for evaluating random equation. So instead of just using one sample, we just generate n different random samples, right? So basically, to evaluate this function, we using the n different random samples. Some cases, some random samples happen to be here, so that this at that case we just treat that this function of f of x has this area. Or we can also generate another random sample like this. Then we actually treat that function has this kind of shapes. But there are n different samples, right? And then since there are n different samples, we need to take the average. In other words, we sum of those n different samples and we take the 1 of n, which is nothing but average. We can call this the actual secondary estimator. But basically, one can easily show that the variance of the secondary estimator, basically it's nothing but original variance of the prime estimator divided by n. In other words, as we had n different samples, the variance of our estimator reducing down as a function of 1 of n, which is very important concept, which is very important property for the Monte Carlo estimator. So I will briefly talk about the mean square error of the Monte Carlo estimator. MSE simply nothing but just basically y hat is our estimator and y is the ground truth. Mean square error MSE nothing but their difference, basically average of square of their difference. And we already know we are using the secondary estimator of the Monte Carlo estimator. So that actually this can be shown as we take the n different samples. Basically, this I is the index of those n different samples. We take their square of their difference and take this average 1 of n divided by 1 of n, and then MSE actually can be decomposed into the bias and variance two terms. I think that is very well-known information for the MSE, but probably some of you already know this one, but basically MSE actually this equation can be decomposed into these two terms. One is actually variance and the other one is bias. Actually, this is a very important concept. If you already took I'm not sure if you already took this machine learning, you might heard about the MSE of some of the machine learning estimator also has the same property. And this variance, nothing but basically this our estimator and one-time estimator, and this is actually average of our estimator. In other words, variance term is the variance here, how far our estimation is away from each average estimator, right? That's why actually this variance indicating that one. And then another term is actually bias. If you look at here, this average of our estimator and this y is ground truth. In other words, bias is nothing but how far the estimation is away from the ground truth. So basically, the variance is that how vary our estimation, and then bias is that on average whether we get the right answer or not. Okay. I'm not going to talk about I'm not really talk about the details about the deriving of this bias and variance of Monte Carlo estimator. Here I will briefly talk about I briefly sketch about the showing the bias, but I recommend you to look for my book for details. Here, actually, this is the I'd like to compute the average bias, basically the average of our estimator. And if you this is nothing but just our secondary estimator here, and then our secondary estimator looks like this: 1 over n summation of the f of xi divided by pxi. Xi is the ith actually random samples, and basically the 1 over n can be get out of this average equation, and then 1 over n, and then this average equation can be this is nothing but like this integration over this one, and then again this summation can be taken out of this integration. Why? This basically assuming that the xi sample have the same this p of x, same this sampling probability. So then we can actually we remove the x of I into the x, then we can cancel up p of x. Then in the end, basically there could be the basically n difference n actually the same function of this n different basically the n of the same function. That's why actually we have n when n divided by n. So that's why this cancel out, and then in the end this is actually this is the I. So in other words, on average, our estimator is correct. We get the right answer. In other words, it's unbiased. We can also derive. You can take the similar concept, similar steps, and then we can also showing that this variance of our estimator has the 1 over n of the 1 over n of the variance of the prime estimator. Basically, again, as we take the n different samples, the variance of these n different samples reduced down as a function of 1 over n over the primary estimator. 1 over n is very important property. Here, I'd like to show some of the example here. We want to compute, we want to evaluate this integration. This very simple integration. So in this case, we can actually have this analytical solution. In this case, integration over the 1 over n, this function will be has the value of 1. Now I'd like to take the uniform samples, and basically at first sample we got the first sample got the 0.86 sum here. Then our estimator. This is our Monte Carlo estimator. Basically, when I mentioned Monte Carlo estimator, it's nothing but the secondary estimator, and then it has a value of the 2.74, which is very away from the 1. And next sample, we got this value here, and then now it gets bigger. It gets smaller, 1.44 and 4, and this third sample, you got the very small value. 0.02, and then our estimator now becomes some value smaller than 1, and now we got this value, and then again now we got this small value, even smaller than this 0.96, but as we take the more sample, it will actually convert to the 1. Here I'd like to show the convergence of our integration. Here this similar function. On average, it should have this value of 1, and this is our Monte Carlo estimator. If we take the first Monte Carlo estimator, we just generate one random samples, and then if we take this number of samples, and then initially you got the very small value, but it becomes bigger than 1 value, but on average it getting close to 1. And basically and then we take another second Monte Carlo estimator. We can take we can also do the same approach. In this case, at first samples, it got a very big value, but it goes down even smaller than 1, and then it becomes very close to 1. But if we actually measure the average, we take their value, we consider n different samples, we take the mean average of them, and then as you can see, it quickly converts to 1 as we gather the more number of samples. And then if we measure the variance actually reduces down like this. You can see that this has a shape of the 1 over n. And I recommend you to try it out. Each sample code, I actually made this MATLAB code, and then if you're interested, you can actually try out this code, which will be available at the homepage. Now we'll talk about the 2D cases. Now the function fx actually has these two parameters, x and y. But our Monte Carlo integration just naturally can be naturally extended to the higher dimension, we just same thing, 1 over n summation of the f divided by p. Obviously, function f and p actually has these two different parameters since it's a 2D domain. Simply speaking, Monte Carlo integration works well for higher dimensions, unlike the quadrature. Basically, it's nothing but we just, even though it has a 2D, we just take the random sample for the xi and yi, and then that's it, just point sample. Even though we had this 7-dimension or 10-dimension, we just take this point sample in that high dimension. That's why actually the Monte Carlo integration very general for handling the high dimensional space. Actually, the random equation also can have the very high dimension, 7 dimensions, even 10 dimensions. So that's why we are using this Monte Carlo integration. Again, basically these are the advantages of Monte Carlo. The convergence rate of our Monte Carlo estimator. Basically, in this case, actually, I'm talking about this. I'm talking about the standard deviation, not variance. Standard deviation has the shape of the big O of 1 divided by the root n. But variance, we can simply use the variance of Monte Carlo estimate has a reduction rate of the 1 over n. It's a very simple concept, right? It's sampling. Also, the point evaluation. We just take we just generate random sample, and then at that point random sample, we evaluate the function fx. Then that's it, right? We take the average, right? It's a very general concept. Works for high dimension. Also, it can deal with the very arbitrary function that has a discontinuity and very odd shapes. I'm not going to talk about the details about this importance sampling, but actually there are techniques known as importance sampling. Its main idea is that we take both samples in the important region. In other words, the important region actually where the function actually has a very big values. Then we can show that the variance of our variance of this importance sampling can have more faster reduction rate than just using the uniform sampling. Okay, so far I talked about the sampling approach, Monte Carlo technique for solving the random equation. So along that line, I talked about the Monte Carlo integration, and I talked about each estimator and each bias and variance. And next time I will use this Monte Carlo integration for solving the random equation. Okay, next time I will talk about Monte Carlo ray tracing, which is actually nothing but path tracing. Just general homework, go over the next lecture slide, watch 2 video or browse the 2 paper, and then write down your summary and submit them online before the every Monday class. That's it. Thanks so much. Bye.